So we talked a little bit about this before we went on break, but I want to come back and just go from the beginning. Make sure we're all on the same page with what's going on here with z-scores and using normal distribution. So the first thing is kind of explaining again what a z-score is and what a normal distribution is. Okay, so with a normal distribution, so let's say we collect this data, we plot it, maybe use a histogram, we recognize it's symmetric, okay? When we recognize that it's symmetric, that means it's normal to us right now. And let's say it falls on this curve right here, okay? And let's make this that curve right there. So let's say that we're maybe talking about, let's say, no, I don't. Let's say it's just talking about like average hours spent on your cell phone in a day, okay? Let's say high school seniors. And the mean is 3.5. The mean is 3.5 hours, and the standard deviation up there you see is 0.3, so 0.3 hours, okay? What we know about that curve, we could use some calculus to determine probabilities of that curve. So what would be the probability that somebody uses their phone for 4 hours? Or what's the probability they use it less than 4 hours? Or more than 4 hours? Something like that. Or what's the probability they use their phone between 3 hours and 4 hours? We could ask those questions. But it's very difficult asking those questions with that particular curve. So what we do is we take that mean of 3.5 and we're going to, so let's see here if we can match these up real quick. So we take this mean of 3.5 and we're going to adjust it and make it become 0. And then we're going to take the standard deviation of 0.3 and we're going to adjust it and make it become 1. Okay? And once we do, that's called standardizing. So that takes a score of like 4, so 4 hours, okay? And it will move it over here on this red curve to somewhere on that red curve. Does that make sense? Okay? And that's called standardizing. That's what a z-score is. A z-score essentially tells you where that individual piece of data falls in comparison to the rest of data, mainly in comparison to the mean, okay? But that is what we're doing when we find z-scores. Does that make sense to everybody? Okay. Now, like I said, we might, and let's just go ahead and find the z-score of this situation here where we've got the mean being 3.5 and the standard deviation was 0.3. So if I had, let's say 4, so finding the z-score, if you guys remember the formula for this, and I apologize for, I don't have all my programs back yet. But a z-score formula is equal to x minus mu over standard deviation. So I said a data point of 4 hours minus mu was 3.5 hours divided by a standard deviation of 0.3. So let's see what that is. So 4 minus 3.5 divided by 0.3. That makes sense. It gives me 1.67. That's my z-score. Okay, 1.67. So when we look at this right here, an x value, a data value of 4, which would show up right there on that green curve, right? That data point is transferred down to x equals 1.67 right there on the red curve. Does that make sense to everybody? So the area then to the left of this green curve, from that 4 to the left of it, that area is going to be identical right now to the area left of this line right here, this 1.67 line underneath the red curve. Does that make sense? We know a lot about this red curve, and we can use that information to tell us about all of these different, infinitely different green curves. Okay, and that's called standardizing. So that's what a z-score does. Now, when we talk about the notation here, okay, the probability that x, my random variable, is less than x. So right here, I'm asking the probability that my random variable is a number less than, for that problem, we're talking about 4 hours for cell phone usage, okay? That is hard to answer that question, okay? What is easier is to convert that 4 down to a z of 1.67. Now that one is easier to answer, and that one can be answered using a table like this. Or if I want 1.67, we talked about using this table the other day. I accidentally closed that. Okay, so with this table, the z-score table, the column over here says z is going to be out to the tens place. So I'll be able to find 1.6 here somewhere. Now, this is negative, so I'm going to go find the portion of my table that is positive. So 1.6 would be right here. And now the hundredths place is up here. So 1.6 meshed with 0.07. I find where that row and that column intersect, and it gives me that number right there. So 0.95254. Does that kind of make sense to everybody? What that would mean is that the area, so 0.952, let's say 0.953. So that means the area underneath this red curve, okay, left of this vertical line would be 0.953, or 95.3% of the total area. Does that make sense, everybody? Likewise, if we go back to, so I had this as 0.3, and this was 3.5. Okay, so that means the area to the left of 4 here, underneath this green curve, so that little region right there, that would also be that 0.953 area. Does that make sense? Okay. So taking our raw data, figuring out the curve that attaches to it, and then standardizing that curve to get it down to this one, to this red one, and being able to interpret that red one allows us to tell us everything we need to know about this one. Okay, and that's what this whole process is about. But there are different types of questions that they can ask us. Okay, every one of these z tables that you're going to come across is going to be cumulative from the left. Okay, meaning that these numbers throughout the table are representative of the area to the left of some z-score. So right here, we've got a z-score of 1.15. So what I do is I go find the 1.1, and I find the 0.05, and I'm going to match those up, see where they intersect, and they intersect right there at 0.87493. That 0.87493 is representing this blue area over here. Okay, 0.87493. Okay, everything that we do with the z table is going to be cumulative from the left. So it's going to be always this situation here. No matter what I want, can I make this A? Hold on a second. See if I can. I don't know if this will attach to my algebra sheet. Now they don't reference each other. Oh, yeah, they do. Awesome. No, they don't. It won't let me change it as I slide that value. But as you change all of these, so I can change this to, 0.4, 0.3, 1.3, but all of these, when I'm asking the z-score, all of these are from the left up into the z-score. Does that make sense? Okay. Now, there's a little bit of a misnomer here with GeoGebra because they're saying x right now, right here, my random variable instead of a z. But I know I can replace that with z because right now I've got my mu set to be 0 and my standard deviation to be 1. So that gives me my standard normal curve. Okay. But there may be times where I want to know, I might want to know that area instead. And the table does not have that area. Does that make sense? Okay. So let's say, so I think the z-score we were talking about in the example is 1.15. Okay. So the area over here we're seeing, it gives me back to be 0.1251. Okay. How do I find that area? Does anybody have any ideas, suggestions?
Yeah. We do the z-score for the white part and like subtract.
Okay. So the so the table will give me the z-score for what's white, right? Okay. So that is this number right here. Okay. And if I take the complement of that, so 1 minus 0.87493, the complement of that will give me now that area that I'm looking for. Does that make sense? So the table gives you cumulative all the way from the left up to your z-score. And if you take the complement, that will give you from your z-score to the right underneath the curve. Yes?
Can you do the negative one too?
Okay, so if we go negative 1.15.
Yeah. I don't remember if that's what I did on the test, but whatever I did, it worked.
Yeah, that'll work. Because of the symmetry. Now, I think it can get confusing maybe when we're talking about a between statement, if I'm using that technique. But if I go negative 1.1 and then 5, so that's 0, 1, 2, 3, 4, 5, 0.12507. So GeoGebra rounds it to the 4th decimal. But yeah, that'll work. Because with symmetry, if z is 1.15 and I have z as negative 1.15, that area there and that area there have to be the same because of the symmetric property. Okay, so if I want to find z-score of negative 0.24, okay, again, your z column is going to give you precision out to the tenths place. So I try to find that tenths place precision, which is right there. And then the row up here is going to give me my hundredths place precision. So 0.04 would be the row I'm looking for, or the column I'm looking for. And now we just see where does that row and that column intersect. And it's at that number right there, which in this case gives me 0.40517. So that is then that blue area, right? Is that okay with everybody? So if I want to find the blue area, okay, cumulative up to a z-score, that comes directly from the chart. That's the easiest. If we want something that is to the right, okay, a lot of times we'll call this like a left tail, okay, because they call this part here the tail. Does that kind of make sense? We talked about tails when we talked about skewed left and right. This is a lot of times called the left tail. This here is referred to as the right tail. If I want to find the right tail, it's the complement of what is inside the chart. Okay, so if I had a z-score here of negative, or not negative, I think it's 1.23, a z-score of 1.23, you see that the chart is going to give me 0.8907 back. So again, 1.2, and then there's 0, 1, 2, 3, so 0.89065. So I've rounded that to 0.7. So that's this area here. And then to find this right tail, I'm going to take the complement, and it gives me 0.1093. Okay? So what that means to us then is there is a 10% chance, or 11% chance, if we want to round a little bit, that whatever this data is representing, that the z-score is greater than 1.23. Okay, so let's go back to we said we had the scenario where when we find a z-score, it's x minus mu over standard deviation. Right now, I know my z-score is 1.23. X minus mu, let's say mu again, we were talking about 3.5 hours use of our cell phone, and our standard deviation was 0.3. So if I go ahead and multiply that stuff out, 1.23, I'm going to solve for x here. So times 0.3, and then I'll add 3.5. So I get 3.869 as the number of hours. So basically what I'm saying is that this z-score here of 1.23 correlates to 3.869 hours in regards to raw data. Does that make sense? So there's 11% probability that I can randomly choose somebody out of this population, and it's 11% chance that they spend more than 3.869 hours on their phone during that day. Does that kind of make sense? What we can do with this information? We cool with that? So we can find a left tail and a right tail, but what if we want to find the in-between? Okay, so we'll find that blue area. We've got these two z-scores of negative 0.75 and 1.23. Okay, if I find I'm just using the information that we already have from the previous problem. If I try to find the probability that goes with a z-score of 1.23, okay, that probability gave me 0.8907, I believe what it was. 8907. Does that make sense, everybody? So everything that I have hash marks here through, that entire area is 0.8907. But I don't want all of that area. I just want that blue area, right? So what did I just do with this image when I do that? Am I removing that area? Does that kind of make sense? Okay. So do you have the ability to find the area associated with that red shading? I can go to my chart and find the area attached to negative 0.75, right? So let's go to that chart. Negative 0.7, and then 1, 2, 3, 4, 5. It's the sixth one because this first one starts with 0, so the sixth one. So 0.22663. 0.22663. Okay, so this is the area associated with the z-score of 1.23. This is the area associated with a z-score of negative 0.75. What can I do with those two areas to find that blue area? Subtracting. So 0.8907 minus 0.22663, and we get 0.66407. Now, we have, and I want you to be able to do this with our table, being able to run through that process with the table. But at the same time, I want us to be able to use technology. Now, when we're using technology, and I don't have a problem with us using it, but the table needs to be learned as well, because you might get into, depending on what your field of study is, you might get into a mathematics course where you're doing advanced statistics. Okay, so I took a class in college that dealt with probability and statistics with calculus. Okay, at that point, like, it was understood that I know how to read one of these tables. Does that make sense? And we had to use a table. The professor wouldn't let us use calculators. So if I have to use this table in an advanced course, but that advanced course isn't going to teach me how to use the table. Does that make sense? That's what this course is for. So you can't just say, well, he's going to let us use the technology. I don't need to learn how to use the table. I want you to use the table because you don't know where you're going to be 2 years, 3 years, 4 years down the road. But what's nice about this is you can type in, so you see these, don't know if I can make those bigger. Yeah. So you see these three little boxes down here, right? I can click those. So this one here, and they're using interval notation here, if you remember that from college algebra or algebra 2. But that is showing basically cumulative from the left. If I click this one on the far right, it's right-sided. Now, when I click them, it changes this down here. But if I change that, because it looks like it's all shaded now. If I change that to a 1, you can see there that we're shading to the right. The one in between, okay, that's showing a between statement, okay? So we wanted between negative 0.75 and 1.23. It's 0.664. We found it to be 0.664. Does that make sense? Okay. Obviously, the technology takes all the thought out of it, right? Okay. There's not a whole lot we had to do there other than type in our z-scores. Okay. Now, that's using that mean and that mu. Let's do this real quick. So if we had the situation where we said we had a mean of we had a mean of 3.5 and we had a standard deviation of 0.3. That was our scenario with cell phone usage, right? If I have a z-score of negative 0.75, let's see what that actual raw data value is. So it'd be x minus 3.5 over 0.3. So I will multiply that out. So negative 0.75 times 0.3. And then I'll add to it 3.5. So a z-score of negative 0.75 is a raw data x value of 3.275. Does that make sense? Okay. 1.23 was our other z-score. So 1.23 equals x minus 3.5 over 0.3. So we'll do the same thing there, 1.23 times 0.3, and add to it 3.5, which we already did this one. A z-score of 1.23 gave a raw data value of x equals 3.869. 3.869. So this is, remember now, this is in hours. This is in hours. When we're talking about z-scores, there's no units there on z-scores. Does that make sense? Okay. But what happens now is we're looking at, I don't know if I still have them here. Okay, good. So right now, we'd be looking at between, so if I'm looking over here, it's going to be kind of nasty looking overlap here, but I think you'll be all right with it. So we had a 3.275. 3.275 is less than x is less than 3.869. Okay, so that blue area right there underneath the curve is exactly the same as the blue area between negative 0.75 and 1.23 over here. That area right there and that area right there are the same. Does that make sense? Okay. We can prove that with this calculator because we can actually change. So keep your eye on, so remember this number here, 0.664, right? That was standardized. That was very easy to do from the table. But if I change my mu to 3.5, change my standard deviation to 0.3, and now look at the z-score between, I think it was 3.275 and 3.869. 689, nope, 869. Is the same 0.664? But now you see up here, the picture doesn't really change. You don't see it shifted. All you do is you see the x-axis be relabeled. But that now, instead of the normal curve being centered all the way over here at 0, it's now centered here at 3.5. Okay. This is very hard to do with, finding this area is very hard to do with a mu that is not 0. So we make our mu 0, everything else adjusts as well, and then we can use these tables, or like I said, we can use the calculator as well. Does that make sense? I think it'd be useful for you. I'm going to show you also how to use Excel, but Excel doesn't provide, I think having the graphic on GeoGebra here is useful. Excel doesn't provide the graphic, okay?
Is it free? Is it cost for
GeoGebra is free. I want to do an example, and we'll be done. It says a personal computer is used for office work, at home, research, communication, personal finances, education, entertainment, social networking, and a myriad of other things. Suppose that the average number of hours a household personal computer is used for entertainment is 2 hours per day. So when it says average, it's 2 hours per day. What is that in our problem when we're doing z-scores? When it says average, that is mu. So mu is 2.5. Okay. It says assume the times for entertainment are normally distributed in the standard deviation. I don't know what I'm doing here, but the standard deviation, that doesn't really flow well. I should say probably for this is half an hour. But standard deviation is 0.5. Okay. It says find the probability that a household computer is used for entertainment between 1.8 and 2.75 hours. Okay, so that's how we would write that. Probability that they're going to use the computer between 1.8 and 2.75 hours for entertainment. Okay? Now, that's hard. Doing that, we would have to look at 2.5 was mu, 0.5 would go 1.8, and what did I say, 2.75? 2.75. Now the calculator allows us to do this and we get 61%, okay? But I want to do this by hand, okay, without the use of GeoGebra. So it's very hard when that's an X, when it's raw data. So what we need to do is we need to transfer that into a z-score and transfer that into a z-score. Okay, so your z-score formula is X minus mu divided by standard deviation, right? So the z-score for X being 1.8, so we go 1.8 minus 2.5, divided then by 0.5. So 1.8 minus 2.5, divided by 0.5. And it gives me negative 1.4 is less than, now this X has become a Z now, okay, because I'm standardizing it. And then 2.75, all that happens up here is that 1.8 now becomes 2.75. So I go through that formula, 2.75 minus, I don't know why I'm typing that in, you can do that math, 2.5 divided then by 0.5, and I get 0.5, or sorry, 1. Okay, is that doable? So now I'm going to look up on my table negative 1.4. So negative 1.4, so it's 0.08076. 0.08076. And I'm going to look up a z-score of 1. Which is 0.84134. And I should be able to do what with those two numbers? I'll subtract them. So negative 1.4 would be about right there. And a z-score of 1 would be about right there. If I subtract this, so this negative 1.4 is that area there. This z-score of 0.84314 is all this area from all the way to the left up into this point. If I subtract those, I should get 0.84314 minus 0.08076.
No.
I get that. Is that right? Let's see here. So when we had, so I said earlier a 6 point, but I had the wrong. No, I didn't have the right mu.
You wrong the whole time.
But mu is 2.5, right? No, mu is 2. Sorry. That's still not right. So we wanted to go between 1.8 and
No.
2.75. Was that right?
You get them for kids too?
All right, we're running out of time to where I can fix this, but we'll pick up with this tomorrow. No new homework tonight.